Alright, so today's video lecture is actually going to take us to some topics that we've already discussed a little bit. We're going to be talking about other forms of energy, energy transformation, and the law of conservation of energy. So, law of conservation of energy, of course, should be incredibly familiar. It says that energy isn't created and it's not destroyed. It can only be moved in and out of a system, and a lot of the times that occurs via energy transformation, where work is done and puts energy into a system, or the system does work and that energy is transformed into another form and leaves the system. And we're going to talk about what some of those other forms of energy are, those other forms that are not mechanical energy, and we're going to talk about how this can be calculated using the law of conservation of energy. Okay, so I think the first place to start is that there are more types of energy than just kinetic and potential energy, which are predominantly the only two forms of energy that we've worked with at any length in the class. When we say mechanical energy, we mean the sum of kinetic and potential energy of any system at any point in time. And we've talked about when this mechanical energy is and is not conserved. And we're going to focus today on when this mechanical energy is not conserved. So there are a whole bunch of different types of non-mechanical energies. Non-mechanical energies would be not kinetic energy and not potential energy, and these include electrical energy, nuclear energy, thermal energy, and chemical energy. So the first thing to say is that while we consider these non-mechanical energies, they are not some nondescript energy type. And in fact, if we get down to the atomic level and we look atomically and subatomically, what we end up finding out is that all of these types of energy are actually just types of kinetic and potential energy at the atomic level. For example, thermal energy is just the energy, kinetic energy of individual molecules in a system, and chemical energy is just the potential energy due to position of different molecules inside of a bond or different atoms inside of a bond. So a little bit more specifically, to give you a more specific definition or understanding, it says, according to atomic theory, the thermal energy is just the kinetic energy of rapidly moving molecules. So let's go ahead and let's break that down into a system that you are familiar with, the air. In the summer, we would say that the air is cold. And what we're really saying is that air lacks heat. That air does not have a lot of heat to it. It's lacking some thermal energy. So what does that mean at an atomic level? Well, at an atomic level, if thermal energy is just the motion of molecules and it's not very warm outside, then that must mean that the molecules in the air are not moving very quickly. And that's exactly what it is. In fact, temperature is just a measure of the average motion of all particles, and that's why you can use different temperature scales. But the SI temperature scale is centigrade and Kelvin. Food energy and fuel energy. So when I say food energy, think the things that you eat, think the things that cows eat, think the things that sharks eat, anything that can be digested. And also fuel energy, so that's octane, butane, propane, rocket fuel, jet fuel. It's just potential energy, that's our U here. It's just potential energy due to relative position of atoms in a molecule. It's stored in the bonds. So that means that in order for this potential energy to be used to do work, the bonds actually need to break or be removed so that they can release energy, and then those molecules, the atoms within the molecules, will rearrange, and their final form will have less energy potential than the original form. So that occurs in a chemical reaction. And so I did a little bit of a visual here. You see, this is just the chemical reaction of the formation of water from hydrogen and oxygen. Anybody that's ever experienced hydrogen gas or knows anything about the history and function of hydrogen gas knows that it's highly flammable, highly explosive, and that's because these bonds right here actually contain a very large amount of potential energy. It's a very big potential energy. So when it's given an opportunity to combine and react, these bonds, the position of the two relative hydrogens, are broken, and they recombine so that each two hydrogens is attached to one oxygen. And when this happens, the potential energy here, the big potential energy here, and the smaller potential energy of the oxygen combine together to get the total energy. Alright, but here, even though there's the same number of bonds overall, the potential energy of this bond and the potential energy of this bond actually equal less potential energy than originally given out here, and that energy is then released into a system, and if there is no energy transformation being done, then most of that energy is released as thermal energy, which is why we think of hydrogen as flammable or explosive. It releases a lot of heat energy when the bonds rearrange like this. So that's to be said that energy can be transformed from one form to another. In this example, chemical potential energy, the energy associated with the position of these bonds, was transformed into another form. In this case, we talked about it being thermal energy that left the atoms. That thermal energy is not within the atoms. It's burning your face off right now. Most often, energy transformation occurs from energy goes from one object to another. When it goes from inside of these bonds to outside in the environment and burning your face off, which is why you wear face protection when you do chemical reactions. That's another way of saying that energy is conserved because the negative work on one object, this object did work. These atoms rearranged their bonds, and therefore when they did work, that energy left them. The amount of energy that left them ends up being the positive energy or the positive work that was done on the environment, this energy over here. So this is another representation of the conservation of energy. So if the conservation of energy is still our key theme, then it shouldn't be surprising to say that we're going to be focusing on that definition, the law of conservation energy. The total energy is neither increased nor decreased in any process. That absolute number, whatever number we calculated at the beginning, must still be that number at the end. We might have to go find it. It might have left the system. It might have left the bonds in the form of heat, but we can find it. It's still there. It exists somewhere. Energy can be transformed from one form to another, and it can be transformed from one object to another, but the total amount remains constant. Let's think about a situation in which this is true. When you put gas in your car, that gas is then combusted. The chemical potential energy gets transformed into thermal energy that heats your engine, and kinetic energy of the gas, which causes an expansion in your piston. That expansion in your piston then cranks your shaft and causes an increase in kinetic energy. In this case, it's specifically rotational energy, which then moves your wheels and does work on the car. Now, engines only have an efficiency of about 35%, which means only 35% of the energy that was released from the potential of the fuel actually got used to move your car forward. The rest of that energy was lost due to dissipative forces, the heat that caused your car engine to get warm, the friction that caused the warming or heating of your individual pieces as they rubbed against the floor, or as they rubbed against each other and they rubbed against the road. But we could find every single bit of potential energy in the system, or around the system. So energy conservation with dissipative forces. We're going to be solving problems, and most of our problems from here on out, we're going to have to be considering whether or not conservative and non-conservative forces are working. It's very easy to say that in most situations we first try to ignore friction so we can understand what happens in a simple version of something, but under most circumstances there's just not going to be a situation where there's not friction, which means that most situations we're going to have to on some measure consider our non-conservative forces like friction. Even in a free fall situation, eventually we might have to consider the drag or the air resistance, which is a frictional force that's caused by the air. So, our previous equation, we said that WNC equals change in potential plus change in kinetic, which if I wrote that out the way that you're going to see it, delta U plus delta K. And then we said that if we can ignore friction, then the change in potential and the change in kinetic is going to be equal to 0. And that's where we got the mechanical energy at one point will be equal to the mechanical energy at the second point. And that only works when there's no non-conservative forces. However, when friction acts, potential and kinetic energy will decrease across a process instead of remaining constant. So let's take a look at that visually. If only conservative forces are working, what do we see here? Right? If only conservative forces are acting, then that means the change in the potential plus the kinetic will always be the same. The change in potential and kinetic will equal 0, which means that if I add potential and kinetic together, it will be the same number every single time. So if E represents our total mechanical energy, that amount will remain constant. And that occurs because as potential energy decreases, kinetic energy increases in that same amount. So that means that at any point in time, if we added this and this for, we'll call that time 1, they'll equal that amount. And if I add this plus this, and we'll call this time 2, it'll equal that amount. And this plus this, we'll call that time 3, will equal this amount. Right? Only conservative forces are working. So even though the energy types are changing, there's a transformation, the total will remain constant. However, if friction is acting, then our total mechanical energy is going to decrease over time. And that means that at any point in time where we investigate our potential and kinetic amounts, they'll equal the total mechanical energy. And that total mechanical energy is actually going to be decreasing. Now, this does not break the law of conservation of matter, because the only form of energy that's actually decreasing is mechanical energy. The total energy is still conserved, just no longer in this system as mechanical energy. Another form must exist in this situation. Right? So that means that frictional forces reduce the mechanical energy but don't get rid of the total energy. Friction always produces heat or some version of heat and light as part of the electromagnetic spectrum. Our thermal energy is what gets produced. So when things heat up, that's energy being transferred from a system. Think of your Indiana Jones example. His feet caught fire because he was transforming kinetic energy into thermal energy. So frictional forces act and energy is still conserved. However, it's not conserved as mechanical energy any longer. And so here's our visual representation of that. Our total energy will always be the conserved mechanical energy, and energy of this TE is thermal energy that results from friction. So our total energy is still conserved. It's just not all in the system anymore. Our system actually has a decreasing amount of mechanical energy, and our thermal energy increases by that amount. So that means that if I took at any point in time along the process, if I wanted to investigate the amount of thermal energy created as compared to the amount of mechanical energy, and I added those up, I would still see that my energy was conserved. The total would remain that constant number throughout the time of the process. And so that gives us a new relationship to consider. The thermal energy made by friction is going to be equal to the work done by friction. Remember that work equals Fd cosine theta. So if friction's doing the work, then we're going to need to know the displacement. And that work, according to the work energy theorem, is going to be equal to the thermal energy that's made. So we can take a look at our equation where the non-conservative forces will equal the change in kinetic and the change in potential. And we said before, when we got to neglect our non-conservative forces, this work equaled 0. But now we're no longer ignoring them because friction is acting. So we have work of a non-conservative force equals negative friction times displacement. What happened? Well, I took the cosine of 180, which is always the angle at which friction acts, and I got a -1. So that's what the work of that non-conservative force is, negative force of friction times displacement, where d is the distance over which the friction acted. So now, if I plug this in for work, and I plug in 1/2 mv squared, and I use the change formula for kinetic and mgy for gravitational potential energy, then I get that the work done by friction is equal to 1/2 mv2 squared minus 1/2 mv1 squared for our change in kinetic energy, plus mgy2 minus mgy1 for the change in potential energy. And here we're of course looking at change in gravitational potential energy. If I rearrange this equation just like I did to bring all of my initial and final, remember we used to have, when there were no non-conservative forces, we said E1 equals E2, but now we have this value here that we're going to move over so that it's a positive value. And now we have, what is this? 1/2 mv1 squared plus mgy1. Hey, that's E1, right? U1 plus K1. So that's what this value right here represents. And then I have 1/2 mv2 squared plus mgy. Hey, that's E2, or U2 plus K2. And then I have a third value here, which is the force of friction, or W and C. So that means that this equation right here, rearranged, is E1 will equal the total work in the system plus the work done by non-conservative forces. And that actually makes sense. That represents exactly what we see here. E1 in the system was equal to the total energy. But as friction acted and the mechanical energy decreased, if we took into account this amount, we would still get that total constant value. And that's represented perfectly by this equation, whichever way that it's written. All right? And this is always going to be true for a system acting with gravity and friction. If we were looking at a system that was acting with spring energy and friction, then of course we'd just replace gravitational potential energy with spring potential energy. So that means that when other forms of energy are involved, like chemical energy or electrical energy, the total amount of energy is always going to be conserved. So even if our force isn't friction, we can still use this equation as long as we know what the work done by the non-conservative forces is. And that makes this a universally valid law, or a law that's true all the time, every single time, is that energy is conserved, or the total amount of energy, that amount will remain constant, whether it's in the system as mechanical energy or just look somewhere in the system and its surroundings in some form as energy. It will always be conserved. So here, let's look at a situation where there's work energy versus energy conservation. All right, so we have two types of equations. You might be wondering, when you use the work energy theorem versus when do you use energy conservation? So the work energy principle, remember, is that the work done is going to be equal to the change in energy. And the conservation of energy says that the total energy at any one point will either be conserved in the system or conserved within the system and the non-conservative forces. When you use one form versus when you use the other. They're actually basically just two different versions or rearranged versions of the exact same equation. And so what it really comes down to is what are you studying or how are you solving the problem? Because you can apply either one of these concepts as long as you do so correctly. And so here's what we're going to consider. If you choose a system and there are external forces, which are of course the forces outside of the system, and those external forces are acting, doing work, then you need to apply the work energy theorem. The work will equal the total done by the external forces. And the change in energy will be the total change that occurs to the system as a result of that outside force. However, if you choose a system and there's no external forces acting on it whatsoever, then you can use the conservation of energy, which, like I said, this is really just you're doing the exact same concept, but you're applying it differently depending on what your system is. So let's consider the spring connected to a block as it's shown here. Our spring has a spring constant K and our block has a mass of M. If we said that this were a frictionless table, and we have two options. We could choose just the block as our system, or we could choose the block and the spring. If we choose just the block as our system, then the work done on the block by the spring is going to be equal to the change in kinetic energy of the block. So that would be the work energy theorem, where we said that the work on the block is going to be equal to the change in kinetic energy of the block. And so that would be where we were only looking at a block system. And that would work, and it would give you a correct answer. Energy conservation would not apply to the system because if the block is your system, then that means that this spring is going to be an external force that does work on the block. It applies a force to the block. So you would have to use work energy theorem here because the energy is not conserved within the block. Something is doing work on the block, adding energy into the system. If, however, you say that the spring plus the block is your system, and now we say there's no friction acting, so that means that here we can use conservation of energy, where W and C equals 0. And now we can use conservation of energy. The energy at the first instant the system acts is going to be equal to the energy at the second time the system acts. So that means that E1, if we first compressed the system in, that means that all of the energy in E1 would be potential energy stored within the spring. And at the end of the system, when the spring is completely relaxed, there's no more spring potential energy, so that means that all of the energy would be in the form of kinetic energy for the block. And so that's an example of how we could either use the work energy principle if we consider just the block and work is being done on the block, versus conservation of energy where we consider the whole system and there's no external forces, so the conservation of energy stands. The energy that was stored in the spring gets transferred into the block. And the thing that makes this really nice is it really is what suits your fancy. How do you prefer to look at the situation? I personally like to use conservation of energy whenever possible, even if that means that I also have to consider non-conservative forces. If, however, you prefer looking at things from a work energy perspective and where the forces are acting or what sources there are, then go ahead and use the work energy theorem. Just be very specific about your system and what you're trying to solve, and make sure that your procedure matches your goal. So, the conservation of energy is going to apply to all systems where no work is being done by external forces. The conservation of energy will also apply when non-conservative forces are acting within a system, but you must account for them. So here's a basic breakdown of how you could solve any problem moving forward using conservation of energy, and a lot of the times this is going to be a simpler procedure than just solving for problems using forces, dynamics, and kinematics. So the first thing that you're going to do that hasn't changed from what you've always been doing is you're going to draw out the situation. A lot of the time, even if you're not using dynamics, if you're not solving with forces, free body diagrams are still going to help you make sure that you're considering everything that's acting and what should be in a system. It will also sometimes help you identify your conservative and non-conservative forces. So don't stop drawing free body diagrams just because you're not specifically doing a dynamics problem. The second thing you're going to do is you're going to decide on a system for which the energy will be conserved, objects and forces. All right, so if you're going to use conservation of energy, which I'm going to recommend, you always want to figure out where is the energy being conserved into. And you also want to identify if there's what forces are acting, because if gravity is acting, then you're going to have gravitational potential energy. If an elastic force or a spring force is acting, then you're going to have elastic potential energy. If friction is present, then you're going to have to figure out the work done by that non-conservative force. So it's always very important to not just figure out which objects are going to be a part of your system, but what forces are acting. Then you want to figure out what you're solving for and decide on the initial point 1 and the final point 2 positions. Because energy is conserved, so that means that within a system, you're going to have to compare one to the other under most circumstances to get any sort of actual usable value. If the object that you're using is changing height, choose a convenient reference point to set to y equals 0 for potential energy due to gravity. The lowest point is always a good choice, and that doesn't have to mean the lowest point that exists. You can consider the lowest point that the object is going to reach during your study of the situation. You could set that point to 0, and that's always going to be my recommendation. If springs are involved, always choose the unstretched spring or the relaxed spring to be your x or y equals 0. It's going to make your calculations much simpler. This is even true if you have spring potential energy and gravitational potential energy. And then you want to apply conservation of energy. Remember that your conservation of energy law depends on whether or not conservative forces are acting. If there are no non-conservative forces, no friction, no work done by non-conservative forces, then you're going to use the conservation of mechanical energy, or the total mechanical energy at the beginning, KE1 plus PE1, is going to equal KE2 plus PE2. And remember, I could always be writing that as K plus U equals K plus U for position 1 and position 2. However, if friction and other non-conservative forces are acting, then the non-conservative forces, the work done by them, will equal the change in kinetic and the change in potential energy, which will also be written as equals delta K plus delta U. I don't want you to get tripped up by that symbology. So, a few things to consider, and the nice thing is that you could do this intuitively, right? If the work done by non-conservative forces is positive, that means that the total energy goes up. A situation where that might be true is if you light a fire to add heat to something to make it go more, that would be a situation where you did positive work on a system. However, if friction is acting or something is acting to overall remove energy from the system, then negative work done by non-conservative forces will reduce the energy. Positive work done by non-conservative forces will equal positive energy. This is a battery to a machine. This is friction to a roller coaster. And then once you've figured out this and you've done it intuitively, you can solve for any of your unknowns. So let's go ahead and let's take a look at what that looks like with example 613, friction on a roller coaster. So a few things that we're going to look at is we're going to say that the total distance traveled is 400 meters. That's important because there is friction on this roller coaster. In this situation, this roller coaster that starts with an initial velocity of 0 travels a horizontal total distance of 400 meters, and by the time it's 25 meters up from its lowest point, it's run out of velocity, which means that it's run out of energy, and that's because of friction. So we're going to actually estimate the average friction force on the car if we're going to assume that the mass of the car is 1,000 kilograms the whole time. So as you can see, I've drawn this out. One thing that I can remind myself as I look at my forces is that friction is acting the whole time, and it's always opposing the motion of the car, which is always forward. Gravity is always acting, and there's always also a normal force. So one of the things that tells me is that when it comes to rising and falling, dynamics might be a little bit of a challenge if I didn't want to have to figure out sorry about that, if I didn't want to figure out what my normal force was every single time. So what I want to do is I want to decide if I want to use the work kinetic energy principle or if I want to use conservation. And looking at this, considering doing conservation is definitely the best possible thing to do. And so this is going to be a roller coaster Earth situation where I can use the equation non-conservative force done by non-conservative forces is going to be equal to the change in kinetic plus the change in potential energy. And I'm going to choose my initial and final positions here. In my initial position, I am going to assume the problem says that the velocity at the top is 0. So my mechanical energy at the beginning is entirely the potential energy of the object right there, since its velocity is 0. And in the second situation, I could say that my entire mechanical energy, because it stopped going up at this point because it's out of velocity, my entire energy, mechanical energy at the second point, is going to be equal to the potential energy at that point. And so what I could do is I could say that I know that the last thing is the work done by non-conservative forces, which is equal to the negative the force of friction times the displacement. And since this equation will apply to our situation, I'm going to rearrange it, and I'm going to say K1 plus U1 equals K2 plus U2 plus the work done by non-conservative forces. I know that for my position 1 and my position 2, there is no kinetic energy. So I know that U1 is going to equal U2 plus the work done by non-conservative forces. So that's going to be mg H1 equals mg H2 plus the force of friction times 400 meters. Now, you might say the work done by non-conservative forces here was a negative, and I set it up over here as a positive, and that's because when I plug it in this equation, if I plug that in, that was of a negative there, which is why it ends up being a positive over here. So now I can actually solve for this because I have mg 40 equals mg 25 plus FR 400 meters. I rearrange that and I get 40 minus 25 mg is 15 times 9.8 times 1,000. So that I have 1.47 times 10 to the 10 to the 5th equals force of friction times 400 meters. So the force of friction average throughout was actually 367.5 or 370 newtons the entire time. Now, I was able to figure that out without needing to know what the kinetic energy at any point along the way was. I chose really simple positions. I could have solved it down here by equating the potential and kinetic energy down at the lowest point, but I didn't need to. And so this just shows how incredibly simple finding an average force of friction, if we assume that it's acting the same way the entire time, can actually be in a problem like this. One of the things to remember is that, like, while this is a guideline for approaching any problem, don't think of it as a prescription or like this is how I'm always going to step 1, step 2, step 3, step 4. There is a great deal of creativity that you're going to need to do, and that's really just going to come from practicing these problems. And so make sure that you take a look at the problems that you're supposed to be doing with this, which are problems number 51, 53, and 55, because the confidence in applying this method, which is incredibly straightforward and going to yield you with some exceptionally more straightforward calculations, right? That expertise and that confidence that you're going to feel is only going to come from practicing.